In our last video, we looked at the heat equation. We used a method called separation of variables to solve it. And in this video, we're going to look at probably the second most well-known PDE, which is the wave equation, which in this case, we can think about it modeling the displacement of a wire vibrating up and down. So let's write it down. I'm not going to go too much into the derivation of it because this isn't a physics class. So we've got two time derivatives now instead of one, and we've got some constant, some positive constant alpha squared, and then similarly to the wave or to the heat equation, we've got two spatial derivatives. So this is for x between 0 and L, some string, and positive time. We have an initial condition, or boundary conditions rather. So the values at 0 and L are going to equal 0 for all t. And now because we have two time derivatives instead, we need two initial conditions. So we have u of x0 equals some function of t for 0 between x and L, and now we're going to need a derivative on here, so du dt at x is 0 equals some other function of t, g of t, for 0 between x and L. So having the two derivatives, or the two initial conditions, the u and the du dt, is just like having our initial conditions for a second order equation having, y and y prime. So this is our initial boundary value problem, modeling the wave equation on a wire. So just to say a couple more things about it, this guy here relates to the properties of the string. The boundary conditions being at 0 are the ends of the string basically being held fixed. And then because I didn't really write this down here, u, where should I write this, is the displacement of a string at location x and time t. So let's say we have something like this. We have an x, let's see, and some length L, so this is some x in here, and then this gives us our u of xt for some time t, and then, our string is going to look something like this. So that's our model, and we're going to look for solutions to this basically the same way we did the heat equation, and a lot of it's going to be really exactly the same, so we won't even have to do the work again. So let's see. To solve, we are again going to assume that we can write u of xt times some function of x times a function of t. And that, if we do our derivatives, if we plug this into the equation, then we get a of x. On the left-hand side, we had two time derivatives, so then that just gives us a b double prime. And on the right-hand side, we had our alpha squared, and then two x derivatives, so that's a double prime of x b of t. We can separate the t's on one side and the x's on the other, and we get b double prime over alpha squared b of t equals a double prime of t over a of x. And that then gives us, well, for the same reasoning that we talked about before, these are going to have to both be constant. And so we'll write it as a negative lambda, and that gives us two ordinary differential equations. A double prime of x plus lambda a of x equals 0, and b double prime of t plus alpha squared lambda b of t equals 0. Now for x, we have the same exact boundary conditions that we had on our heat equation. And so by the exact same reasoning for the heat equation, we get that this only has non-trivial solutions for the eigenvalues lambda equals n pi over L squared, n equals 1, 2, etc. And then our eigenfunctions, the non-trivial solutions are Cn sine n pi x over L. So that's pretty nice because it suggests that we might be able to do the same, find our solutions in the same way for the heat equation because we've got the same eigenfunctions. But now our T equation is different than we had before. So let's figure out what the solution to that is. So now plug the lambda equals n pi over L squared into the b of t equation, which is right up there. And so we get b double prime of t plus, alpha n pi over L squared times b of t equals 0. So with a little bit of scratch work, you should be able to recognize that this is, the same sort of equation that we had for A, that it's a second order constant coefficient, blah, blah, blah. So we can use the characteristic equation. The roots of the characteristic equation will be complex because we have this positive number here. And so that means that our solution will look like b of t. And actually we get a new solution for every n. So we have bn of t. I know we need two constants, c1 and c2, but we're already using c, so let's use d, which depends on n and a 1. So we get d and 1 cosine of n pi alpha over L times t plus dn2 sine n pi alpha over L times t. Now, if it's not clear to you why these are the solutions bn, think about it and try to solve this equation here, because that's the sort of thing that you should be pretty comfortable with solving by this point. So now going back to our u, we get n different solutions, un xt, which will equal an x times bn of t, which will equal the cn sine n pi x over L times dn1 cosine n pi alpha t over L plus dn2 sine n pi alpha t over L. And we can combine these and shuffle things around and get new constants. And we get this. And cosine n pi alpha over L t plus bn sine n pi alpha over L t times sine n pi x over L. And then, of course, linear combinations of the UN are also solutions. So we would just need solutions that some linear combination of these UN that satisfy the initial conditions that we were set with F and G. So that is to say, we consider solutions of the form u of x equals the sum from n equals 1 to infinity of the an cosine sine t terms times our sine x term. And then we will find the coefficients, find the an and bn by plugging in initial conditions. So if we plug in u of x0, so t equals 0, that's going to kill off the sine term, and the cosine part will be 0, so we'll just be left with the sum from n equals 1 to infinity of an, and then the part outside of the bracket, which we've left alone because x is still x, so we get an sine n pi x over L. So that looks familiar. And we need this to equal f of x, or 0 between x and L. And then our derivative, du dt x0. Now we can take the derivative with respect to t termwise through this series. And so the stuff in the brackets, probably don't even need the brackets. The cosine term will turn into a sine and then go away when we plug in t equals 0. And so then the sine term we'll get, if we take the derivative of that, we get n pi alpha over L times bn. Cosine of 0 is 1 times the stuff outside the brackets, n pi x over L. And this is all equal, not to f, to g of x for x between 0 and L. And again, go through and sort of verify those computations that I just did. So we can get the a end and b ends. Again, we've just got our sine terms here. These are exactly the same eigenfunctions that we had before. So we can get the an and bn if we know the Fourier sine series representations of f of x and g of x. So if you have a problem like in the homework where f and g are just, already written as signs, then this is really easy. You just read it off right from the function. And so then one more note to say that these solutions are this u of xt that we found is a formal solution, sort of meaning that we've done sort of the form of the problem, but we haven't really done the analysis of when this converges. Don't yet understand convergence, etc. But we will get into that. And so that is sort of the last example that we're going to do in this section. And we'll go on to talk about the Fourier series in a little bit more depth in section 10.3.